Okay, hi and welcome to a set of video notes on systems of equations. That's vague, isn't it? Meaning it can be any type of equations. Well, for this video, because of where we're at, really linears and absolute values. But we're going to focus on solving them by algebraic means and then also graphing. So let's take a look at what this might look like. You can see I set it up here so that we can look at both versions, both algebraically and graphically for solutions. And we'll talk about the process here in a second, but here's the system. And we can see here that our system has an absolute value and it has a linear function there. And something should pop in your head. But I've never done a system with an absolute value and a linear. I've done a couple linears before, but what does it look like when there's an absolute value in a linear? More importantly, what does the solution look like? Well, let's take a look. So what does a solution look like for this type of system? And really, this could work for any type of system. You just have to kind of visualize what these functions look like. We know that an absolute value looks like a v. We know that a linear function looks like a line. So let's put them together and see what we could get. Well, we could have the scenario where the line intersects the absolute value at one solution. Might look something like this. There's a couple various forms of that, but usually something about a parallel line, maybe a portion of its parallel, because otherwise it would intersect somewhere else. But there's probably some version of parallel involved there. Well, it could also be that it has two solutions where it intersects more than once, because an absolute value has that V shape, has symmetry. So there's a possibility that it could intersect it twice. Could even do it on a horizontal line, and we could get similar but opposite answers, right? Additionally, just like linear functions, if we could have them parallel to intersect once, we could have them be parallel and intersect an infinite number of times all along where they overlap. We could have that. Finally, we could also have the scenario where there's no solutions, again, involving some type of parallel lines where they don't intersect. So, if you consider that, you've got a couple different cases of possible solutions here, and so we have to keep out for them. Visually, that's easy to do, but when we talk algebraically, that means we're going to have to check our answers and see if they make sense by plugging them back into our equation and seeing if it has a true statement at the end, meaning does it make sense? So let's start by doing this algebraically. Algebraically, this isn't different from when we solved linear systems, right? With a linear system, we solve for one variable, then we substituted one variable or whatever that expression was equal to back into the other equation, right? That gave us the ability to have just one unknown, and we could solve at that point. Now, we're going to add in a new rule here, two new rules actually. The first new rule is going to be you have to use the rules of the function. Linear functions are easy. We're comfortable with linear rules. With absolute value, we know that when we solve for absolute value, that we had another rule to get things or the variable that we're trying to solve for outside of the absolute value, right? We first had to isolate it. Then to remove the absolute value, to get outside of it, you had to do a negative version of that equation and a positive of whatever was inside the absolute value. So we're comfortable with that rule. So we're going to employ that here. And then once we're done, we're going to have to check for extraneous solutions, meaning solutions that may fit over here. Maybe we only have one solution. So one, and if we get two solutions, because we're going to be separating our absolute value into negative and positive, maybe one of them doesn't make sense. Maybe they both make sense. Maybe we find the case where every solution is a solution. So we're going to have to check our answers. So let's do this. So in this case, we've picked an easy one because our variables, our absolute value, or I guess one variable or both variables have been solved for. So all we have to do is substitute. So here's what we're going to do. We're going to take this absolute value because it's equal to y, and we're going to replace it in the other equation where we see y. So this looks something like this. The absolute value of x minus 1. Actually, let's put this over here. The absolute value of x minus 1 equals 2x plus 4. And we just replace that y with x, the absolute value of x minus 1. So now that we have that, we got to ask ourselves, now we're going to follow, so we solved for one variable and we substituted into the other equation. Now we're going to fall under the rules of whatever functions we happen to be working with. Well, since we're falling under absolute value, we're going to solve for the absolute value. And the absolute value, you'll notice, is isolated. There's nothing on either side, so it is isolated at this point. Let me fix that up again. So since it's isolated, we're going to attempt to get this x outside of the absolute value by removing it and making one negative version and one positive version of it. So what does that look like? Well, we're going to take what's inside, remove the absolute value, and we're going to make it negative. The negative quantity of x minus 1 equals 2x plus 4. And we also have the possibility of a solution as one positive version of this what's inside the absolute value. So that's going to be x minus 1. We don't need parentheses because positive 1 is not going to change it when we multiply by it, to 2x plus 4. We're going to solve both of these. So in this case, I can distribute the negative or divide it. I'm going to go ahead and distribute it. So I'm going to end up with the negative x plus 1 equals 2x plus 4. Okay, and then let's finish this off. I've got x's on both sides. I want to go ahead and try to keep these positive, so I'm going to move this x here by adding x to both sides. That's going to remove it from the left, and I'm going to get 3x down here. At the same time, I'm going to move the 4 to the other side by subtracting it. Those are going to turn to 0, and I'm going to have to do the same to both sides. So I'm going to get negative 4. So positive 1 and negative 4, drop down my equal sign, is going to give me negative 3. And we can see there that's something we can solve in our head. We're going to find out that x is equal to negative 1. That's one of our possible solutions. And let's solve the other one. So in this case, I've got 2x and an x. So I'm going to combine, trying to keep it positive. So I'm going to move the smaller one to the one with the larger x value, the larger coefficient. Those are going to turn to 0 on the left. And again, since I've got my x's going to the right side, I'm going to move my 4 to the left. So I'm going to subtract 4. Subtract 4 again. Those are going to be removed from the right side, so I'm going to end up with negative 4 and negative 1, which is going to give me negative 5, and 2x and negative x is going to give me x. So there are my two possible solutions. I don't know if they're both solutions, and I don't know which one is. So now we're going to have to check those solutions. So we're going to plug them back into our original equation that we started with. So I'm going to switch colors at this point. So let's do that. So instead of putting x this time up here, I'm going to put negative 1. So I'm going to put the absolute value of negative 1 minus 1 equals 2 times negative 1 plus 4. Now I'm going to follow this out and see if it makes a true statement. The absolute value of negative 1 and negative 1 is going to be the absolute value of negative 2 equals 2 times 1, which is negative 1, which is going to be negative 2, plus 4. This negative 2 and the absolute value is going to become positive, so I'm going to have a positive 2, and a positive 4 and a negative 2 are going to make positive 2. So that does make a true statement, so this is a solution. Okay, let's check the other one the same way. So we're going to take the absolute value of negative 5 minus 1 equals 2 times negative 5 plus 4. The absolute value of negative 5 and negative 1 is going to be the absolute value of negative 6. 2 times negative 5 is going to make negative 10 plus 4. This is going to become a positive 6, and hopefully you're seeing a problem here because negative 10 and positive 4 are going to make negative 6. So what this says is this is not a solution. So what we're thinking in our head, since that's not a solution there, is that we must have some form where there's an absolute value, and we have a linear function that must be intersecting only at one location. And that's what we're going to go ahead and see when we graph these. All right, so let's solve this a different way. Let's solve this visually using a graph. So with this graphing one, we got to remember some of our techniques for absolute values. We could make an evaluation table here and plug in values, but let's try some of our techniques with absolute values. In absolute values, we know that we have the vertex form. And in the vertex form, we know that the generic form of it looks like this, where a is our value that's a scalar, so it multiplies, sometimes considered the slope, that our value that's addressed to the h, or inside the absolute value, that's going to move us left or right, the opposite of what we think, right? Positive would go left, negative would go right. These would be our translations. And then k would be positive would go up because that's going to translate our y value, and negative is going to move us down. Really, if we can find the h and the k, it'll tell us where the vertex is at. And then again, we can use the a as kind of our slope. So let's see if we can do that. So let's go back and look at our absolute value. It is the absolute value of x minus 1. There is no k value, which means it's going to be plus a 0. So let's write that back over here so we can see the whole thing. Y equals the absolute value of x minus 1 but nothing out there. So I'm going to put the +0 for my k because I know that I'm not moving. So that's going to give me a portion of my vertex, which is going to give me the 0 for the k. My h is going to be +1 because it looks negative in there. If it was a -1, this would look like a positive. So I've got my hk, so I've got my vertex. Don't forget that absolute values have symmetry. So from this vertex, if I can figure out what my slope's going to be, and that's the a value, in this case I don't have a value other than 1, so that means my slope is going to be 1 over 1. So I'm going to use this point, the vertex, and then I'm going to use slope going in and use the symmetry going in both directions to graph this. So let's do that. So let's go to 1, 0. I'm going to go right 1, up none, which puts me there. And then I'm going to do my slope from this, right, knowing that I've got symmetry going up over 1 and right 1, up 1, over 1 in both directions from it. So I'm going to get my absolute value. And I like to do a lot of points. Sorry, you'll have to bear with me for that. So let's sketch in a nice little line here. Keep it as true as possible. So there's my absolute value. And now I'm going to go back and I'm going to attempt to graph my linear function. So my linear function, let's copy it down, 2x plus 4. So I'm going to write it right here. Y equals 2x plus 4. This one's a little easier for us. We can see the slope here is 2 over 1. So I'm going to write that in, 2 over 1. And my initial, or my y value, or my initial value is the point 0, 4. So I'm going to go to 0, 4. I'm going to go up 2 and over 1. So let's do that. So I'm going to go to 0, 4. 1, 2, 3, 4. And then if I go up 2 and over 1, that's great, but it's not taking me towards my intersection point that I should have with my linear function here. So instead, I'm going to go ahead and go down 2, left 1, which would be the same thing. And you can see that we landed on an intersection point. So I'm sketching another point there. I'm going to draw my line in so I can see it. And this time, I can see that my intersection point is the point -1, 2. And we can see that here is that we could see that 2, 2 is telling us that that was a solution. Or, I'm sorry, -1, and we found out that the y coordinate here, as you can see it by checking, it would be 2. So -1 is a solution, and -5 is not. So x equals -5. If you look at where that's at, there's 2, 3, 4, 5. There's no solution up there. There's no intersection point. All right, so let's just review everything that you've seen for this video. You should have seen how to solve a system of linear and absolute value, or any functions at that point. It would apply to anything. How to solve them algebraically, making sure to check your solutions because you could have various forms of your solutions. And then finally, you saw graphing both of them and visually what that point would look like. All right, thanks for watching. We'll see you in class.